This is the 7th lecture on the urinary system. In this lecture, I am going to discuss about the reabsorption happening at the distal convoluted tubule and the collecting duct. So this distal convoluted tubule starts from the macula densa. You might be remembering the structure of juxtaglomerular apparatus, which was discussed in a previous lecture. And the juxtaglomerular apparatus is contributed by the afferent arteriole as well as the distal convoluted tubule. The distal convoluted tubule part, the cells got modified and they are known as macula densa. So the distal convoluted tubule starts from the macula densa and the juxtaglomerular apparatus through the renin, angiotensin, aldosterone system, RAS system, control the flow of blood through the glomerulus as well as the rate of glomerular filtration. So from this part, that is the macula densa and the distal convoluted tubule, different parts of the distal convoluted tubule, and the collecting duct has a greater role in regulatory reabsorption. Reabsorption controlled by various regulatory factors like hormone as well as the rate of or the amount of certain substances present in the blood as well as the tubular filtrate. So the distal convoluted tubule starts from the macula densa and it has got from the macula densa, this is a distal convoluted tubule and this is connected to the collecting duct by the connecting tubule, the CNT. So all these parts have a similar type of reabsorption characteristics. And the distal convoluted tubule is adapted to changes in the hormonal as well as the contents of the tubular filtrate in the distal convoluted tubule. And recently the insight gained from the Mendelian disorders of blood pressure and the electrolyte imbalance as well as the studies using genetically modified organisms and gene cloning of the various regulatory factors or the channels present in this part of the distal the nephron has put so many information to us, and now we know quite a lot about the processes happening in this part of the nephron. And distal convoluted tubule can be differentiated into two parts: early distal convoluted tubule or DCT1 and late distal convoluted tubule DCT2. They have slight variations in their functional characteristics as well as morphology, and also the connecting tubule is also different from the distal convoluted tubule in structure, the cellular morphology. The cells of the distal convoluted tubule and connecting tubule has much differences in morphology, and from the morphological differences we can see the differences in their function. So can you assume what differences in function they are good? And we have seen before in the proximal convoluted tubule the cells have a number on the basolateral side of the cell has a number of invaginations which increases surface area of the basolateral membrane, and also that cells in the proximal convoluted tubule has a lot of mitochondria. So what was the purpose of those membrane invagination as well as the mitochondria? The same function is here also. The enhanced number or increased number of mitochondria tell us that there are certain processes happening in these cells which need a lot of energy, which is produced by mitochondria and stored in ATP, and the energy from the ATP is used, like Na plus K plus ATP is present on the basolateral side. Also there is a basolateral extensive network or folding of basolateral membrane. So these two factors, the lot of mitochondria as well as this enhanced surface area of this basolateral membrane, provide the cells a particular peculiar functionality of producing or releasing a lot of energy from the so because of the presence of this membrane foldings, the nucleus of this cell is pushed towards the luminal side, and the luminal side membrane is also has got a number of villi-like projections which increases surface area for reabsorption. So, and when it comes to the cells of the connecting tubule, the membrane's network is quite less, and also the number of mitochondria is also very less, because the processes happening there is quite limited, as the role of these cells or this part of the tubule is just connect the distal convoluted tubule to the collecting duct. And the distal convoluted tubule is an area where most of the regulator reabsorption happens. And you know that the other part of the nephron, and like proximal convoluted tubule and the loop of Henle, many reabsorptions are not controlled by the requirements of the body. Requirements means as and when the requirements are increasing or decreasing. For example, when we are living in a water scarce environment, or we are taking less amount of water, what happens is the body needs to conserve the available water. So that type of conservation, or for this conservation, what need to be done is we have to reabsorb maximum amount of water. That type of regulated reabsorption happens in the distal convoluted tubule, and also calcium reabsorption. When the calcium availability is less, as much as possible, calcium should be reabsorbed from the tubular filtrate. And magnesium, like magnesium reabsorption. All these are regulated reabsorptions, and the reabsorption of sodium, potassium, calcium, magnesium, etc. happen this part under the regulatory control. Most of these regulations are either by hormones like aldosterone, or depending upon the concentration of these substances present in the tubular filtrate. Now we will see the different reabsorptions happening in the distal convoluted tubule. As I said before, the distal convoluted tubule is a shortest segment of the nephron. It's only 5 millimeters in length. So in this 5 millimeters, lot of reabsorption happens, and most of these reabsorptions are active transport. It is quite different from other part of the nephron, where magnesium is passively transported, calcium is passively reabsorbed, etc. But here, when it comes here, most of the reabsorptions are active transport, because these reabsorptions are regulated depending upon the need of the body and the presence of certain hormones and the presence of, or the concentration of these materials present in the tubular fluid. So here sodium reabsorption is driven by this Na plus K plus AT base channel, as in the other part of the nephron, and the BCT as well as the loop of Henle. Here also the sodium reabsorption is driven or started by the Na plus K plus AT base, which move the sodium from the cell, from the epithelial cell into the interstitial fluid. So this is the epithelial cell lining the tubular distal convoluted tubule. From the cell, sodium is moved into the interstitial fluid. From the interstitial fluid, the sodium will move into the blood by the bulk transport mechanism that we have seen before. And along with the sodium movement out of the cell, potassium will moving into the cell. So as a result, the sodium concentration inside the cell decrease. So this decreased sodium concentration drive or cause the movement of sodium into the cell through the Na plus Cl minus exchanger. This is co-transporter, not exchanger. Na plus Cl minus co-transporter. So this is a symporter. Both Na plus as well as Cl minus ions are moving into the cell. So this movement is having a 1:1 stoichiometry. That is, when one sodium ion is moved in, one chloride ion is also moved in. So the movement or the reabsorption through this channel depends upon the chloride reabsorption. If chloride reabsorption is not happening or is not possible, this sodium reabsorption will not happen. So in certain situations, the chloride reabsorption is not possible. For example, if the chloride ions here is very low, or the chloride ions in the cell is high. So when the chloride ions are entering into the cell, they need to be removed from the cell. Otherwise, further entry will not happen because of the lack of the electrochemical gradient or because of the high tonicity. So to aid this or to avoid the accumulating chloride ions in the cell, chloride ions are moving out of the cell into the interstitial fluid through the chloride channels. So this aid in the further movement of chloride ions into the cell, and also along with that sodium is also moving into the cell. And you know that in certain cases we use certain diuretics like thiazide. Thiazide diuretics aims this channel. As a result, sodium reabsorption will be stopped there. Then what will happen? the chloride reabsorption will also decrease. So these are the target of thiazide diuretics. When thiazide diuretics are used for the purpose of treatment or some other purposes, sodium reabsorption is decreased. Along with that, chloride reabsorption is also decreased because the sodium chloride reabsorption is in a 1:1 stoichiometry. And the reabsorption of sodium from the tubular lumen, we have seen that it is depending upon the chloride reabsorption. Along with that, it also depends upon the amount of sodium present in the tubular lumen. So how is that possible, or how is that controlling the sodium reabsorption? When the amount of sodium present in the tubular lumen is high, it increases the Na plus K plus activity. As a result, more sodium will be removed from the cell into the interstitial space, and this will drive sodium movement from the lumen into the cell. Also, the surface area of this luminal as well as the basolateral membrane increases. As a result, more of these channels will be present there. This will also increase the reabsorption as well as movement of sodium from the cell into the interstitial space. So this is how the sodium reabsorption is controlled, and also the sodium reabsorption is controlled by hormone aldosterone. When aldosterone is present, more sodium will be reabsorbed. You will see the function of aldosterone later when we are discussing about the potassium excretion. So in short, 5 to 8% of sodium filtered in the tubular filtrate is reabsorbed at the early distal convoluted tubule. Now we will see the chloride reabsorption at the distal convoluted tubule. The chloride reabsorption, we have seen a little bit about the chloride reabsorption when we were talking about the sodium reabsorption. So this sodium chloride co-transporter NCC. So this helps in the reabsorption of sodium from the lumen in a transcellular route. So the chloride enters into the cell along with the sodium, and from the cell it is moved out of the cell through the basal side by the two channels, the chloride channel ClCKB. So that will help in the movement of movement of chlorine from the cell into the interstitial space. Along with that, another channel called K plus Cl minus co-transporter KCC4. This also helps in the movement of chloride ions from the cell into the interstitial space and from the interstitial space into the blood. So this K plus Cl minus co-transporter, here potassium as well as chloride ions are transported out of the cell. So these two channels, the ClCKB channel as well as the K plus Cl minus co-transfer or KCC4 channel, help in the movement of chloride ions that enter into the cell through the NCC channel, sodium chloride channel, to move out of the cell into the interstitial space. This is quite important. So the NCC channel are moving chloride ions from the tubular space into the cell. So this chloride ion need to be removed from the cell for further reabsorption of chloride through this NCC channel, because that will maintain the electrochemical balance between the cells and the tubular fluid. And in the distal convoluted tubule, more sodium is reabsorbed by ENAZ channel. So that also increase the voltage of the luminal fluid to more negative. So it generates a luminal negative potential. So this highly negative charge causes the movement of chloride ions through paracellular route. So more negative here and more positive here, or less negative there. So this transepithelial negative potential causes the movement of chloride ions through the paracellular route through the tight junction. So how is this controlled? This movement of chloride ions through the tight junction is controlled. This is specific, because you have seen that at different regions of the nephron, the movement of ions through the paracellular route is quite specific. This is maintained, or this is achieved by multi-protein complex, which is formed near or in the tight junction. So the complex of different proteins that controls the movement of materials through this paracellular route or through the space between the cells. Here, the major protein present in this multi-protein complex is chlorine family. Members of the different proteins are present in this family, and different proteins, the different chlorine proteins are present at different tight junctions. Tight junctions at the different part of the nephron. So that decide the ions transport specificity through the paracellular route. So the chlorine protein controls the movement of chloride ions. That is, chlorine form a part of the multi-protein complex which control the paracellular movement of chloride ions. And the movement of potassium and chloride, the chloride through the K plus Cl minus channel, that is KCC4 channel, depends upon the amount, the hypertonicity of the tubular fluid. So when the tubular fluid is hypertonic, this KCC4 channel opens and the chloride as well as potassium ions move into the interstitial space. So the hypertonicity of the fluid decides the opening or closing of the K plus Cl minus or KCC4 channel. So especially in the distal convoluted tubule, the osmolarity of the fluid, the fluid in the tubule decrease up to 100 milliosmoles. So this low osmolarity acts as an inducer for opening this channel, KCC4 channel, and increases the reabsorption of the chloride ions. So now we are going to see another activity that is happening at the distal convoluted tubule, that is the potassium secretion. Major part of the potassium secretion is controlled by a voltage dependent process. Because in the distal convoluted, especially in the distal convoluted tubule, a large amount of sodium is reabsorbed by the Na plus K plus channel. That is a 3:2 stoichiometry extension. When 3 sodium ions are reabsorbed, 2 potassium ions are moving into the cell. So this increases the potassium ion concentration in the cell. That is, the potassium ion is a highly available cation present in the epithelial cells of the renal tubule. So this is voltage dependent. The tubular fluid here is negative, especially at the distal convoluted, later part of the distal convoluted tubule due to the sodium reabsorption. This causes an electronegativity, and a large amount of potassium is present in the cell. This causes a leakage, voltage dependent leakage out of the cell. In addition to this, the flow rate through the tubule also controls the potassium reabsorption. And you can see that in the distal convoluted tubule 1 as well as in the distal convoluted tubule, there is a potassium channel called big or maxi channel, or is also called BK channel. This also controls the flow regulated secretion of potassium. When the flow is low, this BK channel or big or maxi channel is closed, it's not active. As a result, there is no secretion of potassium through the BK channel. But when the flow is high, that is, this shear force of that high flow causes this BK channel to open or make it active. As a result, potassium secretion through the BK channel happens. So that is the flow controlled secretion of potassium. And there is another mechanism, or there is another channel called a renal outer medullary potassium channel. This also controls the secretion of potassium. Normally in other cells, this ROM-K is an inward rectifier. That is, it controls or it makes the movement of potassium into the cell in other part, the cells in other parts of the body. Is an inward rectifier. It helps or it controls the movement of potassium into the cell, and it rectifies the potassium deficiency inside the cell in other part of the body. But in the distal convoluted tubule, it causes the movement of potassium from the cell into the luminal fluid, and this is the electrochemical gradient in the lumen as well as in the epithelial cell controls this role change from the inward movement. Now it is moving or it is causing the secretion of potassium from the cell into the lumen. This role change is caused by the electrochemical gradient found in the distal convoluted tubule. And we have already seen that, I have already mentioned that the role of aldosterone in sodium as well as potassium movement. Here, potassium secretion is controlled by aldosterone. Hyperkalemia or decreased volume of blood causes the release of aldosterone from the adrenal gland. This aldosterone reaches the kidney tubule and causes the secretion of potassium ions. When aldosterone is present in the blood, the Romke channel, more Romke channel will be present. Aldosterone ensures that adequate number of renal outer medullary potassium channel is present to enhance the secretion of potassium from the cells into the tubular fluid. And also high potassium concentration in the body caused by intake of food containing high potassium. If you are taking food containing more potassium, this Romke channel activity will be increased. So potassium is secreted in large quantity in the distal convoluted tubule. It is controlled by different mechanisms. One is voltage dependent, negative charge in the lumen cause the potassium to move, because this potassium K plus is the largest number of highly present cation in the cell. So this causes the leak. This electrochemical gradient causes the leak. Second is the BK channel, that is the shear force caused by the high fluid flow rate through the lumen causes the BK channel to open and the potassium will be secreted. And next is the aldosterone, which is released due to hyperkalemia or low blood volume. It causes or it ensures enough number of Romke channels are present, and that causes the secretion. And also when you take food containing more potassium, that also ensures there is more Romke channel. So in that way, potassium secretion happens in the distal convoluted tubule, and also distal later part of the distal convoluted tubule where electronegativity is high in the luminal fluid. The Romke channel as well as the other secretory process is higher. Another important process happening at the distal convoluted tubule is the reabsorption of calcium. About 8 to 10% of filtered calcium is reabsorbed at the distal convoluted tubule, and the reabsorption happens through the calcium channels on the apical side of the epithelial cell. Apical side is the side facing the lumen of the distal convoluted tubule, and this reabsorption is facilitated or actuated by the ATP, the active transport of calcium from the cell into the interstitial space. Through this calcium ATPase channel that causes the movement of calcium from the cell into the interstitial space, and this creates an electrochemical gradient. Through this electrochemical gradient or facilitated by this electrochemical gradient, calcium is absorbed from the lumen by the calcium channel. And distal convoluted tubule is the major area where regulated calcium reabsorption happens. This calcium reabsorption is regulated by the parathyroid hormone. When the parathyroid hormone is present, the calcium reabsorption is increased. Absorbed through the calcium channel enters the cell, and if this calcium remains in the cell, or higher amount of calcium ions in the cell will inhibit the movement of calcium from the lumen into the cell. So this is avoided by the calcium which is entered the cell bind with a calcium binding protein called cal binding. So this acts as a buffer to reduce the amount of free calcium present in the cell. And also this calcium, when this calcium is bound with the cal binding, this complex moves to the basal side and the calcium is escorted out of the cell through two channels. One is the calcium ATPase channel and second is the type 1 sodium calcium exchanger. That is, sodium is taken into the cell while calcium is going out of. This is an exchange. The calcium is exchanged for sodium. So this is a type 1 sodium calcium exchanger. So through these channels ensure that the amount of or whatever calcium is absorbed in the cell or entered in the cell is moved to the interstitial space. From the interstitial space, it will be moved into the blood. And there is another channel called TRPV5 at the apical site. This is also controlled by the parathyroid hormone. When the parathyroid hormone is there, the transcription of this channel increases. So this, as you know, this channel is a protein channel, and when more proteins will be produced when parathyroid hormone is present in the blood, and it enters the kidney. So more of this TRPV5 protein is secreted. The when parathyroid hormone is present in the blood, this TRPV5 transient receptor potential cation channel subfamily 5 member 5 will be present in higher numbers because their translation is increased. More of this protein is produced and this channel number increases. That also the parathyroid hormone, the presence of parathyroid hormone delays its removal or its degradation, and as that also increases the number of these channels on the apical site. This also increases the calcium reabsorption. And also there is another transmembrane protein called clotho. This also increases the number of TRPV5 channels on the apical site. The same mechanism increases the translation or increases the production, channel protein production, as well as reduces or decreases or slows down the removal of this channel protein from the apical site. So more of this channel will be present and more calcium will be reabsorbed. We have seen the different reabsorptive and secretory process in the distal convoluted tubule. Especially most of these are happening or at a higher rate in the early part of the distal convoluted tubule. When it comes to the late distal convoluted tubule and collecting tubule, they have the same morphology as physiological function, late distal convoluted tubule and the collecting duct. So the reabsorption or secretory process happening at this region is quite low because by the time the tubular filtrate reaches this region, late distal convoluted tubule and collecting duct, most of the required materials are already reabsorbed. Only a little bit is remaining. As a result, the reabsorption process happening in the late distal convoluted tubule and collecting duct are very minimum. And also, whatever reabsorption happens here it is highly modulated reabsorption or highly regulated reabsorption. Those substances which are highly needed by the body only are reabsorbed at these places, like reabsorption of water is controlled by the body's requirement of water. And also, this is a site of major site of secretion of hydrogen ions. This hydrogen ion secretion controls the acid-base balance of the body. And we have seen that in other part of the nephron, the epithelial cells are of at each part, the epithelial cells are of the same type. But when it comes to the late distal convoluted tubule, there are two types of cells, intercalated cells and principal cells. They differ in their function. The principal cells help in the reabsorption of sodium and water and secretion of potassium. Mainly the reabsorption of sodium and water and secretion of potassium. Whereas intercalated, the two types of cells present in this part are intercalated cells and principal cells. So they have differences in their function. So the principal cells help in the reabsorption of sodium and water and secretion of potassium. Whereas intercalated cells causes the reabsorption of potassium and secretion of hydrogen. So their function varies or differs. And the water reabsorption, that is another regulator process happening in the late distal convoluted tubule and the collecting duct. And it is under the control of ADH, antidiuretic hormone. Antidiuretic hormone is stored in the neurons of the hypothalamus. These neurons are osmoreceptors. They check or they sense the change in the osmolarity of the blood. It can be sensed by these neuroreceptors in the hypothalamus. As a result, ADH will be released and this will go to the kidney and control the water reabsorption. And hypovolemia also controls the release of ADH. Hypovolemia is sensed by baroreceptors at the left atrium, carotid artery and carotid arch. So baroreceptors are present at these areas and they sense the blood pressure. So when the volume is low, the blood pressure will be low and it is sensed by these baroreceptors and the impulses about this low volume travels through the vagus nerve and it causes the direct release of ADH, which reaches the kidney nephron and controls the regulated water reabsorption that is happening at the distal late part of the distal convoluted tubule and the collecting ducts. So how this ADH controls the water reabsorption? ADH comes and binds with the receptors on the basal side of the principal cells. So the basal cells, the ADH receptors are there. They are also known as V receptors. The ADH comes through the blood and binds with these receptors. This triggers G protein coupled reactive process in the cell. As a result, adenylate cyclase enzyme is activated. This activation of adenylate cyclase enzyme causes the production of large amount of cyclic AMP. This is a second messenger. This induces the protein kinase A enzyme, which is a phosphorylating enzyme. This enzyme phosphorylates the vesicles where these aquaporins are stored. So water reabsorption at the distal convoluted tubule and the collecting duct, late part of the distal convoluted tubule and collecting duct happens through water channels called aquaporins 2. Normally, these channels are stored inactively in vesicles in the principal cells. So when the phosphorylation of these vesicles happens, these channels move to the apical side and occupies there and cause the inward movement of water by osmosis. This osmotic movement of water is caused by the presence of sodium, chloride and urea in these principal cells. So that is because of the presence of sodium, chloride and urea, the tonicity of the cells is higher, hypertonicity, and the water, the fluid here in the lumen, we already know that most of the materials, solute materials are reabsorbed, and there is no reabsorption of water in the loop of LA as well as early distal convoluted tubule. Early distal convoluted tubule is highly impermeable to water. So the tubular fluid is highly hypotonic now. Lot of water in that fluid. As a result, by osmotic pressure or osmotic movement, the water moves into the cell through the aquaporin channels. So the next process happening in this distal convoluted, late part of distal convoluted tubule is the hydrogen secretion and potassium reabsorption. And hydrogen secretion and potassium reabsorption is an active process which is controlled. This hydrogen another important process happening in this region is the hydrogen secretion and potassium reabsorption by the intercalated cells. A large amount of potassium is reabsorbed by the intercalated cell, but the exact mechanism of reabsorption of potassium by the intercalated cell is not known. It might be through this H plus K plus ATPase, active transport. When X plus is excreted or secreted and potassium is reabsorbed, exchanger. K plus H plus ATPase exchanger. This is an active transport. And how hydrogen is produced here at the intercalated cells? In presence of the enzyme carbonic anhydrase, water combines with carbon dioxide, as happened in the proximal convoluted tubule, and forming H2CO3, carbonic acid. This carbonic acid is quite unstable and this splits into H plus and HCO3 minus ions, and this H plus is secreted into the tubular lumen through two channels, that is H plus ATPase channel where hydrogen alone is secreted, and also H plus K plus ATPase channel where H plus secretion and K plus potassium ion absorption is happening. Both these are active process. And the potassium reabsorption here is under the control of the hormone aldosterone. When aldosterone is present, more potassium will be reabsorbed through this H plus K plus channel. And also this H plus secretion by the intercalated cells is an active process, and it is against the concentration gradient. Sometimes the concentration gradient can be 1000 against 1. The concentration of the hydrogen in the cell might be 1 and the concentration in the tubular lumen is 1000. So even at that concentration difference, hydrogen will be secreted. So active transport excretion of or secretion of hydrogen into the tubular lumen. And as I said before, the functional characteristics of a late distal convoluted tubule and cortical collecting tubule are quite similar. They both are involved in the regulatory reabsorption of water, and also the reabsorption of potassium under the control of aldosterone. And also these cells are impermeable to urea. So whatever urea is present in the cell or whatever urea is present in the tubular lumen will not be exchanged. So whatever urea present in the lumen of the tubule will be excreted. So in short, this distal convoluted tubule, though it is very short in length, 5 millimeter length, a lot of reabsorption and secretory process happens, and most of these are regulated reabsorption or secretion under the influence of either hormone like aldosterone or the presence, the concentration of these ions or these materials present in the cell, or the requirement of the body like water reabsorption. When there is a scarcity of water, more water is reabsorbed under the influence of antidiuretic hormone. So by this is the last segment of the nephron where reabsorption or secretion happens. After that, the tubular fluid, whatever is remaining, it reaches the collecting duct. From there, it will be moving out of the kidney as urine.